we're going to illustrate a screening Pew matrix by evaluating ideas generated by students at Rice University for a Design with Disabilities project. The challenge presented was to develop an eating utensil, specifically a spoon, to help kids with arthrogryposis eat more independently. So individuals with arthrogryposis have limited range of motion in their arms and hands, as well as power in their grip. So these individuals are able to extend their arms, but they're not able to flex their arms. In other words, they struggle to bring their hand to their mouth, thus limiting their ability to feed themselves independently. The target market for this project are kids ages 5 through 12 who are in the public schools. Ideally, the spoon should be able to be carried in their backpack, allowing them to be independent during the school day. In this video, we're going to set up and complete a screening Pew matrix for the design of a spoon for kids with arthrogryposis. We identified 6 design criteria: time, transport, ease of use, lightweight, durability, and cost. So for feeding time, the design criteria is to reduce the time in half as compared to eating without a modified spoon. For successful transport, the design criteria is that 80% of the food that is gathered up by the spoon ends up in the individual's mouth. For ease of use, the design criteria is that 70% of pediatric patients with arthrogryposis can grip and use the device without assistance. For weight, the design criteria is less than or equal to 200 grams, which is about equivalent to 2 metal spoons. For durability, the design criteria is that it lasts greater than or equal to 1 year. And finally, for cost, the design criteria is that it is less than $20. Once these design criteria have been established, you can move to the first step of setting up your screening Pew matrix. In this first step, you want to list the design criteria along the left-hand side of the chart. When most design teams at Rice tackled this problem, they had 40 to 50 brainstormed ideas. We've selected 9 for illustration purposes. Solution A attaches to the arm of the child. They use their other arm to pull a string which transfers the spoon from the plate to the mouth. Solution B is a telescoping spoon. You can use a trigger button to extend the spoon and a different trigger to retract the spoon, moving food from the plate to the mouth. Solution C is a device that attaches to the table that gives the child a lever arm to bend their elbow to move the food from the plate to the mouth. Solution D is a 4-bar linkage. When the device is extended horizontally, the spoon is close to the plate. When the edges are pushed in, the spoon extends and delivers the food to the mouth. Solution E is a long spoon with a right angle. The end of the spoon attaches to the glove, which the child can wear, facilitating eating. Solution F is the Winsford Feeder, a commercial product on the market. It's a mechanized device that operates a little bit like a turntable. The plate spins around, the spoon collects the food, and then delivers it to the child's mouth. Solution G is a long spoon, like Solution E. But this one is made of materials that can be bent and molded to fit the particular preferences of the child. Solution H is like a Ferris wheel. Here, a number of spoons are attached around a center axis. They rotate, scooping food from the plate and delivering it to the child's mouth. Solution I is a series of half cups attached with magnets. Here, the child scoops the food from the plate and then transfers the cups up to the mouth to eat. In Solution J, the team proposed using a ball and socket joint. Here, the child can manipulate a lever that moves the spoon from the plate to the mouth. With these described solutions, you can now complete step 2 of setting up the Pew matrix. You'll take these 9 solutions and set them up along the top row of the Pew matrix. The third step is to set a standard. As mentioned before, an existing solution can work. but it's important that you select something that's intermediate in ranking for the established design criteria. Since there's an existing solution on the market, namely the Winsford Feeder, let's go ahead and select that as our standard in the screening Pew matrix. However, we don't know a priori whether this will rank intermediate relative to the design criteria. The fourth step is to fill in the screening Pew matrix. We're going to start with solution F, which is the Winsford Feeder, or our standard. We're going to give this solution zeros for all the 6 design criteria. So in filling out the remainder of the screening Pew matrix, we're going to start with the design criteria, reduction in feeding time. And we're going to ask the question, is solution A better, worse, or about the same as solution F? We determined for solution A to be worse because the Winsford Feeder can automatically bring the next bite to the child, whereas solution A requires the child to perform 2 motions to get the food from the plate to their mouth. So for this reason, we're going to assign a negative or minus for time for solution A. Next, we're going to compare the reduction in feeding time for solution B as compared with solution F. Solution B also gets a minus because this too requires volitional movement for the child and would thus be slower than solution F. So if you look across for all the other solutions, except for solution H, all of them also receive minuses for this very same reason. In contrast, solution H is an automatic mechanism, like a Ferris wheel, that delivers the food to the mouth automatically. For this reason, it receives a 0, comparable to the standard solution. So if you notice, we selected one design criteria and worked across the chart, comparing each proposed solutions to the standard. We have also made our decision based on our best professional knowledge. Next, we'll look at the criteria of transport. Transport is defined as the percentage of food that's gathered up by the spoon and ends up in the individual's mouth. So we'll start by asking the question, is solution A better, worse, or about the same as solution F? So after discussion, we determined it to be comparable, since the arm with the device can rest on the table and should be fairly still and stable. This will allow the food to be transported from the plate to the mouth without a lot of spillage. Thus, we'll evaluate solution A as a 0. So let's consider solution B and ask the question, is solution B better, worse, or about the same as solution F? Now, with this telescoping function, it may be a little jumpy as it retreats, bringing the food from the plate to the mouth. So we might expect that less food would be transported relative to solution F. Therefore, we assign solution B as a minus. We can continue for the design criteria of transport and fill in the remainder of the Pew matrix with plus, minuses, and zeros. In the interest of time, let's skip down to the design criteria of lightweight. If we compare solution A with solution F and ask the question, how does solution A compare with solution F in terms of weight? So it's fairly easy to see that solution A should be considerably lighter than solution F, which we know to be 30 pounds. So we'll score solution A with a plus. If we look across the other devices, all of them will score as a plus because they too are more lightweight than solution F. The exception to this is solution H, which is likely to be of comparable weight. So let's consider the design criteria ease of use. In reasoning through whether pediatric patients will be able to grip and use the device without assistance, the reasoning is very similar to that we discussed for reduction in feeding time. And so the results are similar as well, with negatives across the board with the exception of solution F, our standard, and solution H. For the design criteria of cost, it will be similar in its reasoning and results to the criterion lightweight. The criterion durability looks a little bit different, and the results are shown here. Now the chart is completely finished. we'll sum down each vertical column to determine its score. So step 6 is to reflect on the results. So you can see the solution B has a -2. All the other solutions are either a -1, a 0, or 1, noting that our standard scored as a 0. Step 7 is to select the concepts that move on from the screening matrix to the scoring matrix. Unfortunately, this screening matrix failed to identify poor solutions, hence it failed. So if you look carefully at the numerical results, with the exception of solution B, all the other solutions are compressed. They're basically within 1 point of the standard solution. With a P matrix that turns out like this, you can't really differentiate the solutions. As a result, this matrix failed.